No, sir, not yet.
Huh? You cannot?
No, sir.
I mean, if you cannot see the slides, then maybe just say no or just say what is the issue.
Yes, sir, now I can see.
Okay, there might be some lag, depending on the bandwidth and the frequency and where you are. But is everybody okay with the slides? Is it visible? I mean, you might say no in case it's not visible. If it's visible, then it's okay. I'll assume it's a yes. Okay. All right. So, okay. So let us start. So essentially, I'm going to be presenting things in slides, and then I'll be making a handout out of these and sharing it right after the lectures. So a few technical things. One is that Zoom only allows for 40-minute sessions, which means since we took almost 10 minutes to get things started and set it up, we might continue for another 25 minutes or so in this meeting, and then I'll have to create a new meeting, and I'll send you the ID and the password, which most probably is going to be the same. And then we can rejoin in another 5 to 10 minutes. So I might end up taking 1.5 hour equivalent of classes, essentially meaning 2 meetings for today, and then we'll see how we pace ourselves and so on. Okay. So with that being said, let's start. So today it's going to be essentially solving problems from homeworks 1, 2, and 3. So yeah, so this is officially lecture 20 because I think I had lectured up to lecture 19 in the traditional setup. But nonetheless, this is the first online lecture that we're having. And so let's start. So I already sent out the specific questions that I wanted people to think about and the questions that we'll be discussing. And we'll do it in the order of the homeworks, okay? So this is homework 1, problem 7. And the question says, it has 2 parts, but the first part says, let G be a Lie group of dimension n. So it's a finite dimension Lie group. You have to show that the tangent bundle is diffeomorphic to G cross Rn. Okay, so you should remind yourselves that a Lie group is a smooth manifold, which is also a topological group, such that the group operations, meaning the multiplication and the inverse map, these 2 maps are smooth maps of smooth manifold. That's what a Lie group is. Okay? So we have to show that the tangent bundle is isomorphic to the trivial bundle of rank n, if you want to use the terminology of vector bundle. So this is saying that the vector bundle Tg, which is the tangent bundle, is isomorphic as a vector bundle to the trivial bundle of rank n over the base space G. Okay? But anyway, here we don't really ask for an isomorphism of bundles, but we'll see that in the proof it will turn out that the diffeomorphism is much more than just a diffeomorphism. The tangent spaces go linearly isomorphically to the copies of Rn, right? Remember that Tg is nothing but union of the tangent spaces, Tp of G. And G cross Rn as a set is nothing but the union of P cross Rn, where P belongs to G. So we are going to define a map which maps TPG linearly isomorphically to P cross Rn, and this is a smooth map with a smooth inverse, right? Okay, so most of you who have thought about this question would know what to do. So basically what you want is you want to identify the Rn with the tangent space at identity. Okay, because Rn is of dimension n and the tangent space at any point is also of dimension n. And you might as well choose the identity as a special element and look at T little e of G, which is also denoted by the letter script G or mathfrak G if you're using LaTeX. And that is called the Lie algebra of the Lie group G. So that's going to be our aim, that show that Tg is actually diffeomorphic to the Lie group G cross the Lie algebra mathfrak G. Okay. Okay, so what do we do there? Well, basically the idea is you want to identify the tangent space at any point P to the tangent space at identity. Right? So how do you do that? Well, you have left multiplication, right multiplication, and all sorts of things on a Lie group. So in particular, you consider the left multiplication, L subscript little g. That's a map sending H to GH. Okay. And this is a diffeomorphism because the left multiplication by G inverse is its inverse. And all of these are smooth maps. So what you do is you look at the linearization of DLG inverse. So the linearization is now going to be a linear isomorphism mapping the tangent space at little g to the tangent space as identity. Right? So any questions so far? Okay, good. So what do we want? Well, we want to use this to define the map. Remember, we wanted to identify any tangent space to the tangent space of identity, and this map does it. So you define the map capital Phi, which is simply going to take a tangent vector V at the point little g, and it's going to keep track of where it's a tangent vector at, namely the element little g, and you transform this vector to a tangent vector identity by the linearization of LG inverse. Right? So this is evidently a well-defined map from TG to G cross the Lie algebra. Okay? So if you can show that this map is a smooth map with a smooth inverse, then you're done. Okay. So as we'll see that we'll show actually that this map is smooth, and there's an inverse map which is also smooth, and they're inverses of each other by definition. But one thing you note at the very beginning is that this map capital Phi is actually a linear isomorphism from any tangent space to the tangent space at identity, because DLG inverse is a linear isomorphism, right? So this is already looking like a vector bundle map. So all you have to do is so it's clear that capital Phi is a bijection because of how things are defined. And this will have an inverse. Well, what should the inverse do? Well, the inverse should do exactly what the inverse of DLG inverse does. Remember, LG is the inverse of LG inverse. So D of LG inverse, the inverse of that is D of LG. This is just chain rule. Right? So the inverse is given by the map capital Psi, which starts from the Lie group cross the Lie algebra and maps to the tangent bundle. Well, how does it do that? It takes an element G and it takes an element of the Lie algebra, and all you do is you take the left multiplication action on the vector, and that's going to give you a tangent vector at little g. Right? This is exactly the inverse of Phi. So it's clear that these two are inverses. That's a set theoretic property, but you want to check that these two are smooth. Okay. So that's going to be the remaining part of the question. So are there any comments or remarks before we move to the next slide? Okay, all right. So let's move on. So there are a few ways of maybe understanding smoothness, but let us try a slightly seemingly abstract approach, although it's not quite, because this is a good way of introducing things which you'll see in other courses later on, sections and vector fields and so on. So let's look at the multiplication map, M. Remember at the outset I told you that this is a smooth map because G is a Lie group, correct? Which means if you linearize this map, but linearizing, of course, I mean it's a linear map when I restrict to tangent spaces. Having said that, it induces a smooth map DM, which is a map from the tangent bundle cross the tangent bundle to the tangent bundle. Okay? So at this point, you might object saying that, well, it should really be the tangent bundle of G cross G. It's not TG cross TG. Well, here's the exercise that I have secretly identified T of M cross N with T of M cross T of N as smooth manifolds. And we had hinted at how to do this problem by looking at charts and so on. But if you haven't done that, then this is a good time to do this exercise afresh. So this is what we are using secretly. The tangent bundle of G cross G is canonically diffeomorphic to tangent bundle of G cross tangent bundle of G as a space. So you have a smooth map, okay, from TG cross TG to TG. All right. So now what do we want? Well, we want a map, remember, from the Lie group cross the Lie algebra to TG. So to somehow think of how to insert the Lie group cross the Lie algebra into TG cross TG. If you can insert it smoothly and you can embed it smoothly, then you can apply the map DM and you're done. So you have to insert G in TG, the Lie group G inside the tangent bundle TG, and you have to insert the Lie algebra script G into the tangent bundle TG. That's our, as an embedding. Okay? So if you think about it for a while, you'll see that there is an obvious map from a manifold to its tangent bundle for any smooth manifold. And that map is called the zero vector field. Namely, you take a point P in the manifold G and you send it to P comma 0, where 0 stands for the zero vector in Tg of G. Okay, so this is a zero vector field, which simply means at every point you are assigning the zero tangent vector. And this is well defined, smooth, and everything, and this is clearly an embedding. So this gives you an embedding of G inside Tg. Okay? And this is more than just a smooth map. There is a smooth map which is also a section, meaning when you apply the projection map back from the tangent bundle, you get back identity. Okay? So sections which arise as vector fields, which are nothing but sections of tangent bundles, are important things, useful in other things that we'll study. Okay? Okay, so now what about the Lie algebra part? Well, remember the Lie algebra is what? It is nothing but TE of G, right? It is a particular tangent space inside the tangent bundle. So there's an evident inclusion, which is denoted by little I. So I hope everybody can see on the slides. The little I denotes the canonical inclusion of the Lie algebra, which is the tangent bundle, tangent plane at E inside the tangent bundle, and S0 is just mapping G by the zero section or the zero vector. And then these two are smooth maps. It's an embedding, and then you compose it with DM. So that's obviously going to be a smooth map, right? So what is the big deal about this? Well, the big deal is that this is the composition is nothing but the map psi that we have defined. That is left as an easy exercise for you to check. So this proves that the map psi, capital psi, is actually a smooth map. Okay, because it's a composition of two smooth maps. DM precomposed by the zero section cross the inclusion. Okay. So any questions or comments so far? And I hope everybody can hear me and can at least see the slides. Okay. Okay. All right. So what remains to show is the smoothness of capital Phi. Well, how would you do that? Well, you could try to say that smoothness is a local property. So if I can somehow show that this map Phi is smooth in some neighborhood of identity, then maybe by left translation, I can show that Phi is smooth in all neighborhoods, because a neighborhood of identity when I left translate will give me a neighborhood of the corresponding point G if I left translate by LG. Right? So that would be the usual thing to do. You just do it at one point and use left invariance to take care of the other things so that it does the work for you, rather than in a general manifold you have to choose charts for all points so that everything is covered. So that's going to be the goal. Okay. So you first choose a chart U phi of the Lie group at identity, and you consider the restriction of capital Phi to this tangent bundle TU. Remember, TU is nothing but the tangent bundle of G restricted to the open set U. So this is just the union of TPG, where P belongs to the open set U, right? So if you can show that this is smooth, this map Phi restricted to TU, then that shows that Phi is smooth at identity. And then you somehow want to use left invariance to talk about Phi being smooth elsewhere. Okay? So this is what you want as a first step. So recall that once you have a chart for a manifold, in this case U comma Phi, that automatically gives you a chart for the tangent bundle restricted to U. So I'm calling that TU. So there is a chart TU and the map is Phi tilde. And what is that map Phi tilde going to do? Well, remember TU looks like U cross Rn, because U now has global coordinates x1, x2, xn to the chart. And so any point in TU can be expressed as Phi of x1, x2, xn, the coordinates, and d by dxi, all linear combinations of d by dxx, right? So TU is in effect U cross Rn, which is in effect Rn cross Rn, because you can identify U with Rn. Okay? So that is the map Phi tilde. So this is something we have seen at the very beginning of defining tangent bundles and how it is a smooth bundle. So what do you have to compute? Remember, you identify TU with U cross Rn and identify that further with Rn cross Rn. And on the other hand, you have U cross the Lie algebra, and that can be identified with Rn cross Rn as well, because the Lie algebra is identifiable with Rn and U can be identified with Rn through the map Phi. So effectively what you have to show is that this map is a smooth map. So I'll just give you a moment to look at the map. So this is saying phi tilde inverse. So remember, phi tilde maps TU to Rn cross Rn. So it pulls it back to TU, apply phi, that maps it to U cross G, and apply phi cross identity to U cross G, that simply gives you Rn cross the Lie algebra, which you can then identify with Rn cross Rn if you want. But you want to show that this is a smooth map of the variables x1, x2, xn and the alpha i's. So are there any questions up to this point regarding what exactly we are checking? So we want to check that this is a smooth function of xi's and alpha i's. Okay, so in case you are kind of hesitant but you more or less see the logic, just go back and just revise your notes. And
So shouldn't the range be belong to Rn square?
which one?
There it's phi tilde inverse of that thing. There is a
Yeah.
summation of alpha.
No, so the phi tilde inverse maps what? Phi tilde inverse, remember, first of all, it maps T, it identifies TU to U cross Rn, and then it identifies U cross Rn to Rn cross Rn.
Oh, so it is the intermediate map, not the
No, but you
chart.
just, it is Rn cross Rn only, right? So what in Rn cross Rn, what is an element of T P Rn? It's a point P which I'm denoting by the coordinates x1, x2, xn, and a tangent vector is alpha 1, alpha 2, alpha n. But on Rn, there is a global basis at every point, d by dxi at P. So I'm just calling it alpha 1, alpha 2, alpha n as an n tuple. You can also say call it alpha I d by dxi. But this is alpha I d by dxi at the point x1, x2, xn. So x1, x2, xn is not the coordinates, it's not the points in M. x1, x2, xn is what you get by applying phi to a point P in U. Right? Does that make sense?
Yes, sir.
So that's, I mean, I'm just saying that. I'm saying everything is Rn cross Rn. Just for the last part, if you want to, whether you want to identify U cross script G with U cross Rn, that you do by taking phi cross identity. So then you get Rn cross the Lie algebra. At that point, you can either want to identify the Lie algebra with Rn, or you might stop there because that is just a choice. So you have to just check smoothness up to that point. So we have to check that this is a smooth function of xi's and alpha i's. And one of the first things we check is that this map, when I apply to xi's, alpha i's, the first component is xi's. Okay, because that is almost evident from the maps involved. Okay. So what is xi? So we have to compute what this xi is as a smooth function of xi's and alpha i's. Okay. So how do you compute xi? Well, remember you're given a tangent vector alpha 1, alpha 2, alpha n at the point x1, x2, xn. So in Rn, what should that correspond to? In Rn, that corresponds to the equivalence class of the curve x1 plus t alpha 1 dot dot xn plus t alpha n, right? That is a standard linear curve which is initialized at xi, x1, x2, xn and has velocity alpha 1, alpha 2, alpha n. So that is what you choose in the Rn cross Rn part. You're going to apply phi inverse to that. And then you want to apply this map capital phi. But remember what does capital phi does? It basically says you multiply by left LG inverse, right? And G at this point is phi inverse of x1, x2, xn. This is now a point in the manifold. The first component, you see the first bracket in xi is phi inverse of x1, x2, xn. This is an element of the Lie group. So you want to left multiply by the inverse of this to the curve that you have obtained by taking phi inverse, correct? So there are three inverses. The two inverses with black color are simply the inverses of phi as a map. There is a red bold inverse. That inverse is supposed to be the inverse as an element of the group. Remember, phi inverse of x1, x2, xn is an element of the Lie group. So that inverse is the inverse in the Lie group itself, and then you're left multiplying by that element to the curve. Okay, and then when you take d by dt at t equal to 0, that is what you get as an element of tu, or I'm just denoting it by bracket rather than taking d by dt. But this is what you want to show is a smooth function of x1, x2, xn, and alpha 1, alpha 2, alpha n. But this is smooth because this involves inverses of maps phi and the Lie group inverse. All of these are smooth, and this is evidently a smooth function of the xi's and the alphas. Okay. So that's it. So we'll see an explicit computation of what this is for a particular group. Okay. So this is not going to become identity or anything. So for special groups, this might turn out that the map is x1, x2, xn, alpha 1, alpha 2, alpha n, goes to x1, x2, xn, alpha 1, alpha 2, alpha n. But this is not going to be true in general. Xi is not alpha 1, alpha 2, alpha n in general. But it is smooth nonetheless. Okay. So that takes care of the smoothness for phi. So phi and chi are inverses. So phi is a diffeomorphism. Okay. So yeah, so therefore phi of tu is smooth. So what is left is to show that phi is smooth restricted to any other open set around any other point, right? So yeah, so before we move to the next slide, any questions up to here? See, if there are some computational questions that you are unsure of, it is suggested that you might have a look at the slides later on, and then maybe we can discuss it during office hours or otherwise. If you have any conceptual questions, it's relevant to ask those in these lectures rather than spend time on whether a sign is correct or a sign is wrong, because I might have made some mistakes while making the slides. So I checked it twice already. I fixed the errors that I saw, a few from the morning, but there might still be some errors, but hopefully none so far. Okay. So yeah, so any questions or comments? Okay. So, all right. So what is the method? Well, the method is left invariance or left translation. So for any G in G, how do you obtain a chart? Well, it's simple. You take the left translate of the open set U we had chosen before with G. Let's call that V. What should be a chart for V? Well, it should simply be you take LG inverse. Applying LG inverse to V gives you back U. Applying phi to U gives you back a copy of Rn. So that's going to be the chart, right? So you left multiply the open set, and the chart like you pre-compose with left multiplying by G inverse so that they fit together. Okay. So now, as you might expect from a lot of these things, that there is some diagram that inherently presents itself, whether you like it or not. It's this diagram. So you have the map capital P restricted to TV, map capital P restricted to TU, and you have two vertical arrows. The left one we have already seen, it's the linearization of LG. Since U maps to V, DLG maps TU to TV. And the right one is LG cross identity. So it's just mapping U to V under the left multiplication, and the Lie algebra is just the same. So if we could show that this map is a commutative diagram, this diagram is actually commutative, let's assume that for the moment, then what would we get? Well, you realize that the lower horizontal arrow is a diffeomorphism. We just proved it, right? What about the upper, the, okay, not the upper one. The upper one is what we're trying to show is a diffeomorphism. What about the two vertical arrows? Well, the two vertical arrows are also diffeomorphisms, right? Because left multiplication and D, they're all diffeomorphisms. So if the diagram commutes, that implies that the top horizontal map is a diffeomorphism, and in particular, it's smooth. So we are done once we show that this commutes. Okay. So how do you show something like this commutes? Well, I'll leave it as an exercise, but it simply boils down to this following exercise: that you simply have to check that DLG composed DLH is D of LGH. So if you left translate, see, it's clear that LG composed LH is LGH because of how group elements multiply. You simply have to apply the chain rule and conclude that this is true. Okay, this is simply one line chain rule applied to LG composed LH is L of G. Okay. But this is what you use to show that the diagram commutes. And I'll leave that as an exercise. And then we discussed the last thing already. Since this is a commutative diagram, the vertical arrows and the bottom horizontal arrow are diffeomorphisms. The top arrow is a diffeomorphism. In particular, it's smooth. And since phi is smooth locally, it's smooth globally. All right. So any questions regarding this entire question? Okay. So let's move on to part B. So, okay, I wanted to make a remark. So maybe I'll just make it here since it's already appeared. So the point is, for a typical matrix Lie group, you have the obvious exponential, which is the matrix exponential, right? You just take a matrix A, you exponentiate, and if you choose your A from a particularly nice set, namely like trace 0, that's going to give you determinant 1 when you exponentiate, then you can take it to be a chart. This is by inverse function theorem, okay? And we have seen this in the class. So for a typical matrix Lie group, we could compute the vector xi, which is what we are trying to do earlier, as follows. You take, so my chart is now phi inverse instead of chi inverse instead of phi inverse. So it's the same terminology except that phi earlier is now replaced with chi. Okay, and chi inverse A is e to the A. E to the A here stands for the actual matrix exponential. So if you expand, what do you get? You get chi inverse A inverse. So the inverse of exponential A is exponential minus A. So that's the first term. And chi inverse of A plus TB is e to the A plus TB. So now you want to multiply these two matrix exponentials, and usually you cannot take the exponents in common because the matrices are usually not commutative. If you take two general matrices, they may not commute with each other. So e raised to a into e raised to b is not e raised to a plus b, as opposed to the 1 cross 1 matrices, right? So you use what's called the Baker-Campbell-Hausdorff formula. Most of you have heard of it. If you haven't, it's a very useful formula, but more than that, it's important to know how the formula is derived in general. So it's good to sort of read it up on your own, but you use this formula to expand this, and what you get is something of this form. It's e to the tb minus t over 2, the Lie bracket ab, plus t over 12, the Lie bracket of ab with a, and so on. You can actually write down these exponents, the coefficients, and the bracketing is going to be exactly that. Iterations of a certain number of times followed by b. Okay. So anyway, so what I want is I want to take d by dt of this, right? So at the end, the equivalence class of this curve means I differentiate this with respect to t and set t equal to 0. So if I do that, what do I get? If I do that, what I get is b minus half ab plus 1/12 ab, and so on. So the map that I really wanted to compute in this particular setting turns out to be the vector b at the point a. So a is like my base thing. So b goes to b minus this. It's evident that b is not going to be unless a is 0, right? And remember, a is 0 in the chart means that when you exponentiate the 0 matrix, you get identity. So a is 0 in the chart corresponds to the identity matrix of the Lie group. And only when a is 0, or you're looking at the expansion around identity and at identity, the map looks like b goes to b, because all the Lie bracket of AB, AAB is going to be 0 if A is 0. But if A is non-zero, typically A and B will not commute. So for all those points, B will not go to B. It will have all these extra terms. Okay. So that's, anyway, that's the point. So the function is identity when A is 0, obviously. And for abelian Lie groups also this is true, because for abelian Lie groups, for those of you who know this, the Lie bracket is 0. Okay. So all Lie brackets are 0. So the map is identity and hence, but not in general. Okay. So that's a remark. Okay. Anyway, so I'll be having a few remarks down the line for most of these questions. Some of those are not particularly relevant from an exam point of view, but they are important and relevant for your general sort of edification and learning. Okay. So what about part B? So part B is a continuation of the earlier problem. It says you want to provide a Riemannian metric on the tangent bundle of the Lie group. Well, how to do that? Well, you take the Lie algebra, you produce a Riemannian metric on G by left translation. That is what you have to do. So let's start with the inner product on the Lie algebra itself. So I've denoted it by angular brackets here, and I've put a subscript E, but very soon I'm going to ignore this. This is simply to denote that the inputs are coming from the Lie algebra. Okay. Tangent vectors are E. So what is the definition? Well, the question tells you what to do, really. So it says take two vectors from tangent spaces at little g, apply left translation, which is DLG inverse, and you send it. So this is now a vector at identity, and this is also now a vector at identity. You take the inner product using the given inner product that you've chosen. Okay. So it is clear that this is an inner product, okay, because this is an invertible linear map. So these maps obviously define a map from TG cross G, TG to R. So for those who might have forgotten, recall that we have defined this set TG fiber product G to be all tangent vectors V comma W, a priori lying at different tangent spaces. But there's an identification which says you only look at VW which are at the same point. So it's really like at every point you have two copies of the tangent space TG of G. Okay. So this is precisely where we want our Riemannian metric to be defined on. Okay. So the exercise which I assigned in class, and I'll assign it once more if you haven't done it then, is that this is a smooth manifold. Okay. So to say that this is a Riemannian metric, what you have to show that this map here is a smooth map. Everything else is clear that fiber wise it's an invertible linear map, it's bilinear, it's positive definite and everything, because the original choice is bilinear and positive definite. We have to check for smoothness, right? So how do you check for smoothness? So before I move on, any questions? Okay. So smoothness, again, you want to prove that something is smooth on a smaller set, you prove that something is smooth on a much bigger set. So what is that much bigger set? Well, remember we have done this, we have done the hard work. You have an identification of the tangent bundle, namely this one, with G cross the Lie algebra. And you have two copies of them, so you identify it to two copies of G cross math frac G, right? Okay, so this is a diffeomorphism, correct? Because psi we proved is a diffeomorphism. So the first arrow is a diffeomorphism. Now what is pi 2? Well, pi 2 means you simply ignore, so each map, when I apply pi 2 here, this simply means projection onto the second factor. So I take an element of G cross math frac G, I project it onto this, I ignore where it came from. So what should that give me? That should just produce the Lie algebra cross the Lie algebra. And then I simply evaluate using the inner product, which is chosen once and for all. And this whole map is now a smooth map, correct? Because it's a composition of three smooth maps. Fine. So why is this useful? Well, remember, in this set, so the point is, let me go back one slide. So this set TG cross TG over G, this is a subset of TG cross TG. It's a smooth submanifold, okay? So this map that I have, this will restrict to a smooth map on the submanifold that I just discussed in the previous slide. The only question is, what is that map? What is the restricted map? Well, it's a simple verification that the restricted map is the original inner product that we defined, because we have used implicitly psi to define the map. Okay? So this restricts to the old map, and because this is a restriction of an actual smooth map, the old map is a smooth map. Okay? So there's nothing much here once you have done the part A. Okay, any questions? There's one remark that I'll share, but before that, any questions on this part B? Is the pace all right? Am I going too fast? Or are things working out okay for the video or the audio? Okay, so I mean again the rule of thumb is, if you have any issues, then you should sort of unmute and say no, or what is the issue. I mean, if you're not saying anything, I'm assuming that you're more or less following and there are no technical issues. Okay, so the remark is the following, that remember we had constructed a left invariant Riemannian metric, right? By simply saying you choose something at identity and then you use left translation to go everywhere. You could have also done right translations. There's nothing sacrosanct about left. So you could have chosen a Riemannian metric which is right invariant simply by defining it to be the right translated version of the metric at E. Okay? But quite often one is interested in a Riemannian metric which is bi-invariant. But that simply means that it's a metric which is left invariant as well as right invariant. Okay, it's both. So usually for a general Lie group, you are not going to find very many bi-invariant metrics. It turns out that compact Lie groups do admit bi-invariant metrics. Okay? So we'll see an example maybe, if not in this homework, maybe in one of the later discussions. For those who have taken a course in, say, harmonic analysis, or maybe have seen this, typically the way one proves this is you first of all prove that there is a Haar measure on this compact Lie group, which integrates to 1, and then you use the Haar measure to basically take any metric on the Lie group and then average it out over the Lie group using the Haar measure to make it bi-invariant. That's called the Weil trick. Okay. So compact Lie groups do admit bi-invariant metrics, and the reason why I'm pointing it out is we'll see an example of this, illustration of this rather, in the section on curvature, that for compact Lie groups you can compute the curvatures very nicely in terms of Lie brackets, provided you're starting with a bi-invariant metric. And usually for simple compact Lie groups, there are not too many bi-invariant metrics. There's essentially one up to a scale. Okay? So anyway, that's just a remark for those who might find this illuminating or interesting. But as I said, the remarks are not specifically meant for the actual course and exams. All right. So I think Zoom extended the session. I don't know for how long, but let's see. If we have to stop at some point, then we'll take a break and then start again. Okay. So
Sir, the session is actually infinitely extended. Just a message came up in the note, came up in the screen that the Zoom has modified, updated itself so that like during this crisis time there is no time limit. It can be
Acha.
extended as much as you want.
Oh, that's nice. Yeah, I got a message saying they are extending this, but I didn't see anything. Okay, then that's very nice. So we'll not go on infinitely, of course, but okay. Thanks, Shopnil, and thanks Zoom, I guess. So okay. So the second question, I think this one, well, I wasn't planning to discuss this initially, but I think Ananta and someone else, I forget, I think they asked to discuss this question. So this question says you start with an isometry. So remember, isometry as we defined in class is going to be an isometry in the differential setting, meaning it's a diffeomorphism of the Riemannian manifold. So M here is a Riemannian manifold, M comma G. So an isometry is a diffeomorphism of the Riemannian manifold such that it preserves the metric, meaning that if I want to calculate the inner product of two vectors VW, I can calculate it using G, or I can take d phi of V, d phi of W, and then I can calculate it there in the target M, and they're going to be the same. Okay. So then the question says, show that d phi commutes with the exponential map. So one of the points about the question was you have to make sense of what do you mean by d phi commutes with the exponential map in the first place, because the exponential map once applied goes from a chart inside the tangent space to the manifold. So at the level of the tangent spaces, you cannot apply d phi, right? I mean, you can apply d phi, but you cannot apply d phi at the level of manifolds. You can only apply phi at the level of manifolds. So we'll get to that, what this question actually entails, okay? But let's start with what we usually do. You choose a point P, choose an open set U prime, and you choose U prime such that it's a homeomorphic image of the exponential map at P. So this you can do because the exponential map, as we proved in class, is a local diffeomorphism at every point, right? Which means the exponential map is a map from the tangent space at P to M. Usually it's from an open subset of the tangent space at P around 0 to an appropriate open subset of M containing P. This is what the exponential map does, right? It's not all TPM and the target is not all of M. So if it is all of the tangent space, then that's essentially Hoff-Rino theorem, that M is geodesically complete. So anyway, we know that exponential is a local diffeomorphism. So you can choose an U prime, which is the image of the exponential map of, let's say, some ball around 0 in the tangent space TPM. So that's what I said. U prime is exponential u is an open set where the exponential is a homeomorphism. Okay? So now we consider this diagram again. You draw the obvious diagram. So the first horizontal arrow is phi. The lower horizontal arrow is d phi. The two vertical arrows are the exponential maps. Okay. So now you should look at it carefully. The rightmost vertical arrow is dotted, correct? Which means that map might not be well defined by this choice of u. Remember, we chose our u prime to be something coming from u so that u and u prime are homeomorphic. But for that particular u, you are looking at d phi of u. So d phi of u is going to be some open set in the tangent space at t phi p, correct? So this thing over here, the d phi is a linear map. It's a linear isomorphism. So it's going to map u homeomorphically to an open subset of the tangent space at M of the point phi acting on P, because this is happening at P. This is in TPM. It's going to be in T phi P of M. The point is that the exponential map may not be a homeomorphism on this particular open set. Right? This exponential map has its own open sets where it's a diffeomorphism. So you might have to make this smaller for this to be a diffeomorphism. Is that clear? So because this was something that you chose for P, and then you're applying D. But this may not be the domain where exponential is a homeomorphism, or even defined for that matter. So the rightmost vertical arrow is dotted, as the exponential map may not be defined, as I just discussed. So, well, what do you do? Well, you simply basically want to make this small enough. So you look at the rightmost, the right bottommost entry, d phi at P of u. You want to make this open set small enough so that the rightmost vertical arrow is a homeomorphism. How do you do that? Well, you choose a V small enough so that the rightmost vertical arrow is a homeomorphism, and then you replace u by d phi inverse of that choice, and then everything else works. Okay? So that's what you do. You replace d phi of u with a smaller open set V around phi p if needed, such that the exponential map is defined on V and a homeomorphism. All right? And you redefine U to be the inverse. D phi is already a linear map. So this is the map that you get. Okay, so now this is a perfectly well-defined diagram. So the question is, does this diagram commute? As we saw in one of the earlier questions. Okay. Well, how do you show that something like this commutes? So the top horizontal map is phi, the lower horizontal map is d phi, the two vertical maps are exponentials. So recall that if I start with u, go up, and then go to the right, what does this produce for me? So this exponential map, remember, produces, it is basically the result of a geodesic in the direction of v evaluated at time 1, right? Similarly, when I apply phi, this is going to be the image of the geodesic. What about the lower horizontal map? Starting with an element little v, a vector little v in u, I am taking the image of that on the d phi. That's going to be a tangent vector in capital V. Applying the exponential means I look at the geodesic in that direction, initialized at phi p, evaluate at time 1. Right? So there are two issues with the diagram. One, why does the diagram commute? But even more pressing is the issue of whether the diagram actually makes sense, in the sense whether, whether when I remember that if I go up and then right, this definitely lands in phi of exponential pu. But how do I ensure that when I go right through the bottom arrow and then I go up through the rightmost arrow, I actually land in phi of exponential pu? I might be landing somewhere else entirely, right? So the map has to be well defined, first of all, meaning that it lands in the right thing, and only then commutative diagram comes into play. So there are two issues, as we discussed. I'll let you read this. So what we'll do is we'll tackle both these birds in one stone by proving that it is actually well defined in the sense we discussed, and it commutes by simply working with explicit geodesics and then evaluating at whatever time you want, rather than evaluating at time t equal to 1 directly. All right. So that's going to be the goal. So Any questions? Okay, so what to, I mean, what to do here? So we start with a vector little v in U. So remember, this is a tangent vector at P. You consider the geodesic. This is the notation that we have been using. This is the geodesic initialized at P of P and with the initial vector d phi at P of V. So you look at this geodesic. This is a geodesic. So I probably should have said this before. So this is one of the exercises I had assigned, and if you haven't done it, again I'll repeat. This is a good time to do it. So if you have an isometry, if you take a geodesic and compose it with an isometry, then it's also a geodesic. Okay? So geodesics are mapped to geodesics under isometry. So with this exercise, you can take the usual geodesic that anybody would take, namely gamma T P P, which is a geodesic initialized at P with velocity vector V. You can apply the isometry phi. By the exercise, this is going to be a geodesic. Where is it initialized? It's initialized at phi of P, right? Because you're simply going to apply it at the, so apply at gamma of 0, but gamma of 0 is P, so phi of gamma of 0 is phi of P. Now, what is the velocity vector of this new geodesic? Well, you do d by dt at t equal to 0. But then this is chain rule, right? This is d phi composed gamma prime. What is gamma prime? Gamma prime at 0 is v, and d phi of v is just d phi at p of v. So what do we observe? We observe that the two geodesics, which is phi composed gamma, and the earlier one in the at the last line of the previous slide, they have the same initial conditions, same initialized point, and the same velocity vector. So by uniqueness of geodesics, they are identical, correct? So that tells you that when you evaluate this at t equal to 1, it lands in the right thing and it is commutative. It proves everything in one go. So instead of taking a geodesic and applying p, you could simply take the initial data with respect to d phi and then take the geodesic there. They're going to do the same thing. Okay. So this is not too hard once you prove this exercise, which I'll leave it as an exercise, and it's worth trying. All right. Any questions before we move on to the next question? Okay. So one remark here, the assumption of phi being a global isometry is obviously sufficient, but what you should note is that the argument that we have just outlined will work for any local isometry, because all we need is the geodesic to be defined for small enough time, phi to be a local isometry and everything. So as long as phi is a local isometry, you can show that local geodesics are mapped to local geodesics. Okay. So if you need this local version, sometimes you do, then that's good enough. But typically the global statement is for phi being an isometry, which is what we proved. Okay. All right. So let's go on to homework 2. So this one, problem 7E. So the earlier one was 7B. So there's a small typo in the homework, or at least the version that I have with me. Maybe I fixed it on Wheeler, I didn't check. So I gave the inner product AB defined to be trace of A transpose B, but that is evidently not going to be positive definite because of how SON behaves. So remember, the Lie algebra SON has matrices A of the form A transpose plus A is 0. So if you evaluate inner product AA with the original definition, it would be trace of A transpose A, and then you're going to get trace of minus A square. So I really want the minus sign here. Okay, there's a minus sign, and for what we want to do, this is not going to play an important role, but it is with a minus. Okay. Because what we're going to do, it really matters. It doesn't matter whether this is positive definite or not. All we care about is invertibility at some point, perhaps. Okay, so anyway, so the question is, consider the Riemannian metric obtained by left translation. So we discussed what a left translated metric is at length in the very first question. We want to compute the exponential map at IN. So remember, this is a priori not the matrix exponential, even though it's tempting to say that this is going to be the matrix exponential. The matrix exponential is some map from the Lie algebra to the Lie group. This exponential is the metric exponential, meaning for every Riemannian metric, you can use the exponential maps defined via the geodesics, and that's the map that we are looking for. Okay? So make sure that you understand this distinction. In some nice scenario for compact Lie groups with suitable Riemannian metric, it turns out that they're going to be the same, but you should be aware of the distinction and the subtleties. Of course, in this case, SON is a compact Lie group, so chances are that we may end up doing the same thing, but that's a happy coincidence. Okay. Okay. So we know all this. We know that SON consists of matrices A of the form A transpose plus A is 0. The tangent space at any matrix P can be described as take the tangent space at identity and you left translate. Right? So that if you left translate by P, then the tangent space at identity goes linearly isomorphically to the tangent space at P. Okay, so we start with any A in SON. When we apply this left translation, what do we get? Well, remember the left translation simply means that you look at A as a tangent vector, but really you want to look at A as an equivalence class of curves. Okay, so that's what I want to do first. So given this tangent vector A, you have to give me a curve in the Lie group SON, which is initialized at identity such that its velocity at t equal to 0 is A. But such a curve is nothing but e raised to ta, the usual matrix exponential, right? Because when I differentiate e raised to ta at t equal to 0, I get A, and e raised to ta is initialized at identity. So I'm replacing the vector A with the equivalence class of the curves e raised to ta. I'm left multiplying by p, that's what dLp does. The d simply means you now differentiate d by dt at t equal to 0. Okay. What do we get? I get pa, correct? Because d by dt works only on the e to the ta factor. So if I wanted to evaluate the inner product of two vectors, this is simply going to be inner product pa with pb at the point p, but by left invariance, this is nothing but inner product ab, right? Because you can simply plug in trace here, and by left invariance, I can ignore the p. That's precisely what left invariance does. But inner product AB, okay, there's a minus sign that I missed here, okay. And so the minus sign carries all the way through. So anyway, the point is this is something we know. By left invariance, the inner product PA PB is just inner product AB, which is minus of trace A transpose B, okay. So what we want? So we want to calculate geodesics. So as we discussed with a slightly lengthy introduction at the beginning, that a tempting guess is to claim that e to the ta is a geodesic. Okay. So how do we show that this is a geodesic? Well, first of all, geodesics should have constant speed. So it's good to check that indeed that's true. If you take gamma prime t at the point e to the ta, what do you get? You get e to the ta times a, e to the ta times a at the point e to the ta. So this is actually, yeah, this shouldn't be there. Okay. So this is the typo. Just ignore that when you see the handout. So this is what it is, but by left invariance, I can just knock off this e to the ta's, and I can ignore this. So this simply becomes inner product AA, which is a fixed constant. Okay. So it indeed has constant speed. So that's reassuring. Okay. So remember, we want to show that this is a geodesic, so we wouldn't take the high route of computing the Christoffel symbols and doing everything, because we have a specific geodesic and we want to show that's a geodesic. So calculating all geodesics is probably not very meaningful at this point. So we'll take the easier route of actually doing exactly what we need to do. Okay. So anyway, there's a question which I have maybe discussed in the class or maybe hinted at. So this says that the matrix exponential is a local diffeomorphism. So the map A goes to e raised to a. This is a local diffeomorphism at 0. You have to use inverse function theorem for this. Okay. So anyway, so what we do is you choose a basis of the Lie algebra and you choose a neighborhood of 0 where the exponential is a diffeomorphism. So by the exercise, such a U exists. Okay. What do you do? you look at the vector fields d by d alpha. Remember, these are your usual vector fields in a local chart. If the coordinates are xi, then d by dxi are your vector fields. And they'll form a basis of Ta of u, because u is now inside a linear space. So the tangent space at A is the same thing as the tangent space at 0, and they're spanned by these global vector fields. Okay? So what we really want is to basically compute, so let me just skip this remark for the moment, on this line. So what I'm trying to say here is this d by d alpha at the point A really corresponds to the curve A plus t alpha, where E alpha is a basis. Okay? Anyway, so that's not too important. So we are going to use a specific formula, and again, this is going to be very much related to the first formula we saw in the first few slides, the Baker-Campbell-Hausdorff formula. So this is related to that. This is called the Zassenhaus formula. You can look it up. You can read up or try to deduce it on your own. So it can be derived from the Baker-Campbell-Hausdorff formula. So what this says is that if you expand e raised to a plus tb, and you can of course expand e raised to a plus tb by simply saying this is I plus a plus tb plus a plus tb whole square by 2 plus a plus tb whole cube by 3 factorial, and so on, right? But then the catch is, remember, you want to take d by dt of this, which means you really care about e raised to t times whatever shows up, and any t square, t cube, all those terms you don't really care, because those when you differentiate will go to 0 at t equal to 0. So this is why this expansion is perhaps useful, that it tells you that when you expand it in products of exponentials so that you can apply the product rule, it's e to the a times e to the tb times e to the minus leave bracket ab with a factor of t over 2. The next one is e to the t over 6 leave bracket a ab, there's some order of t square, and it goes on and on. Okay, so I might be off regarding these factors 6 and 24. It could very well be 12 and something else, but anyway, we'll see. And the other ones, as I said, it's order t cube. That, see, what I'm trying to say here is that the third term is e to the minus t over 2 times this. The fourth term is e to the t over 6 plus some t square and t cube and so on. But all of this is part of e raised to this. Same with this one. Okay? So anyway, the upshot is when you take d by dt, you'll get this. Okay. So the only thing that shows up is the coefficient associated to the linear part in the exponent of the exponential. This is simply by product rule, because at t equal to 0, all these factors become identity. So I'll just give you a moment to have a look at it. Just see, apart from the signs or whatever, just see whether if you follow the logical deduction. If this expansion is given, when I take d by dt, whether you can conclude on your own that this is exactly what you get. Okay, if you just give you a minute, if you have any questions or comments, you can ask. Okay. Okay. So this whole huge expression over here, I'm calling f of b. This is really f of ab, but for lack of introducing more notation, it's f of b. So anyway, so as I said, there's a high school way of doing this. You simply expand e raised to a plus tb as a power series, take d by dt, set t equal to 0, and you can, if you're careful enough, take a piece of paper and sit down, give yourself maybe 15 minutes. You can work out the signs, and this is exactly what you're going to get, even by that seemingly elementary method. The reason why I chose to introduce these formulas and do it this way is that some of you might know of these, and it's useful to also know other things which interact with more elementary things, because this is, it's part of Lie theory anyway, whether you like it or not. So anyway, so it's something that you can compute. So what is it? telling us? It's telling us that this is, remember, if I put B equal to E alpha, then this huge expression is what is going to be my tangent vector. So it's going to be very hard to actually compute the Lie bracket. I mean, the inner product of this d by d alpha at A with d by d beta at A, because that would give me the Riemannian metric at A. Once I have that, I can now calculate the Christoffel symbols, and then that's going to be a humongous computation. Although it can be done using some other methods in a more clever way, but this method is going to be running into serious computational issues. Okay? So this is what we want to do ideally, but remember, we have a much more modest goal. What we want, remember, is to show that the radial lines in the chart are geodesics. So what is a radial line in a linear space emanating at the origin? It simply looks like TV, right? If V is a vector, a radial line looks like T goes to TV. So it's a radial line initialized at 0 with velocity vector V. So we simply want to say that these radial lines are geodesic, so that when I exponentiate under the actual map that we chose, psi, then that should be a geodesic. Our map psi that we chose was the matrix exponential, so e raised to T should be a geodesic. That's how we chose the chart U, right? So that is much easy, because whenever we say radial lines are geodesic in U, that means what? You want to take the Riemannian metric on U, expand it in terms of polar coordinates rather than using the usual Euclidean coordinates. So your metric in polar coordinates, if it looks like dr square plus some other terms involving dr d theta or d theta d psi, then you already know that the radial lines are geodesics. Right? So what I'm saying is the usual metric looks like dxi tensor dxi, a sum with some coefficients, and dxi tensor dxj with some coefficients, a sum of that, and it's non-degenerate and positive definite. So when you express this in polar coordinates, if I can show that my metric G looks like dr tensor dr, that's what dr square means, and other terms involve d theta, dr, d theta, I don't care. In the radial direction, this is a constant C. This does not change. Then I'm done. Then the radial lines are going to be geodesic simply by rewriting the geodesic equation in the polar coordinates. So this is something I'd like you to go back and think about. You might have seen this in curves and surfaces or maybe even elsewhere. But this is something not very hard but very useful, that if you want to care about, if you do care about only specific kind of lines and you want them to be geodesics, then this is good enough. Okay, we are not claiming all straight lines in U are geodesics, they are not. But specific straight lines which are emanating radially are geodesic. But then this description of G already tells me that if I write down the geodesic equation and my thing only varies in R, no variance in theta, then obviously the radial line is a geodesic, simply by writing down the geodesic equation in polar coordinates. The x size will be replaced by d by dr and d by d thetas. So it suffices to prove this, okay? So I hope this is reasonably clear. So what would that mean? So that would simply mean that I don't care about an arbitrary B. I really care about the radial line at A in the direction of A, correct? So I'm really looking at E of A plus T A hat, where A hat is going to be the unit vector in the direction of A. I want to show that somehow for those things, when I calculate the the inner product, it's constant. So that's what I want to show. Okay. So effectively, I don't care about d by dt of A plus T E alpha. I care about d by dt of A plus T into the unit vector in the direction of A. So I'll replace b by A hat, and then we'll compute the length. So any questions? Okay. So the first thing that you note is A hat is going to be the unit vector. So as I said, in the direction of A. So what is d by dt? Well, I'm claiming d by dt is e raised to A into f of A hat, but f of A hat is A hat. So I'll just give you a moment to have a look at it. I'll go back into the next slide in a moment. So I'm claiming that this velocity is nothing but e raised to A into A hat. Why is that? Well, remember, I'm replacing B with A hat everywhere. So this is A hat minus half of Lie bracket A hat, 1/6 of these Lie brackets all the way through, correct? Now, what is the Lie bracket of A with A hat? Well, that's 0 because A hat is some lambda times A, and Lie bracket of A with A is 0. So all these Lie brackets vanish because A hat is a linear multiple of A. So I'm left with A hat, just this term. So that's nice. Okay. So which means what? Which means when I calculate the inner product, this is happening at the point A. This is nothing but e raised to A hat, e raised to A hat, because that's what I just deduced. But then by left invariance, this is A hat at the identity. But that is 1 because I've chosen it to be a unit vector, right? So that's it. So that basically says that if you're moving along this direction, you're simply taking d by dr, then you're getting 1. So if you expand the metric radially, you're going to get dr square plus other terms of the form d theta squared, d theta d psi, and things with coefficients. But the radial directions will provide you with geodesy. So when I exponentiate using the map, here I mean the matrix exponential, that is going to be a geodesy. All right. So yeah, so that's the proof. So any questions? Okay, so there's a remark that I want to make. So the remark is that it's clear. If it's not, then just think about it for a moment or two. That the inner product that we have here, minus trace A transpose B, that is also right invariant. Okay. So in this particular instance, the inner product that we have at our disposal is actually left invariant as well as right invariant, because you'll be taking minus A P transpose PB, but then P transpose is P inverse and trace is conjugation invariant, so this is going to be right invariant. Okay. So what we have at our disposal is a bi-invariant inner product, and actually it turns out that a bi-invariant inner product also satisfies an identity of this form. Okay. This is coming from the map capital L, that joint map. So for those interested, you can look this up, but a bi-invariant inner product typically satisfies this. And in this case, you can check it by hand that this is true. This is by cyclicity of the trace. Okay. The trace is cyclic. Trace ABCs, trace BCAs, trace CAB. That cyclicity implies that this is true in our case. So this is a nice property to have for an inner product because this is related to Lie algebra and it's also related to bi-invariance. Okay. So this particular metric has all those properties. So this is not an accidental problem that happens to work out. This happens to work out because of deeper reasons. Well, I mean, we have worked it out without resorting to these deeper reasons, but the point is there's much more to the story than this question suggests. Okay. Yeah, so and the last remark is in general, the matrix exponential and the metric, meaning the Riemannian metric exponential, do not coincide. Okay. Unless the metric is bi-invariant. So that we'll not be able to talk about in this course, but maybe we'll talk about the curvature of a Lie group which has a bi-invariant metric. That is going to be more relevant for us. Okay. So can I move on to the next slide, the next question? If there are no questions on this particular problem. Okay. Okay. Just a second. So this one is a slightly longer problem because it's broken up, at least I broke it up into a few parts, but it's essentially, I think, 2 parts in Docarmo. It's primarily a question of curves and surfaces, but it has a nice mix of ideas involving a lot of things. So although it is really a question in 2 and 3-dimensional geometry, it's a nice exercise to have in a course in Riemannian geometry. So let us go one by one. Okay. So just a second. Yeah. All right. So we start with a regular curve. We assume that f of v is non-zero. So we have drawn this picture in the class in the notes. So if you take the Riemann surface, which essentially looks like a surface of revolution, right? So it's basically f of v cosine u, f of v sine u, g of v. So g of v is the height, f of v is the radius. So you fix a plane at height g of v. On that plane, you're drawing a circle of radius f of v. And then the stack of circles as g of v moves is the surface. Right? So your regular curve here in particular means f of v is non-zero, and f prime v and g prime v are both not zero at the same point. Okay? So that you do not want it to be something which is singular at some point. So f prime and g prime are not zero simultaneously. Another way of imposing that is saying that f prime square plus g prime square is non-zero everywhere, and fv is non-zero. Because you want the radius at height gv to be a non-zero radius, so that it traces out a circle. Just like you have these circles there, it's like how you watch in a video of somebody making pottery, right? When somebody makes a pottery, there is an axis. The axis is the z-axis, which is the axis of revolution, and then the pottery is built by stacking concentric clay sort of circles, so to speak, and the shape changes. So, but it's essentially a surface of revolution. That curve is given by FBGV. So that's exactly what this is. Okay, so the first question is, show that in local coordinates P, U to S, the Riemannian metric is of this form. Well, this is a simple computation. So let's just go ahead and do it. So the coordinate is U comma V, because U comma V already gives you a chart, locally at least. So of course, you cannot take U to be more than 2 pi, because then sine and cosine are periodic. So whenever u is between 0 and 2 pi and v is appropriately chosen, in fact v could be chosen to be r, it's a chart. So with those coordinates, this is f square. And so essentially when I say g11, I mean guu or maybe gvv, we'll see that. So 1, 2, 2, 1, these means the coordinates uv. Okay. So what you have to compute? You have to compute del u. That's going to give me G11, right? So, well, how do you do that? You just simply calculate d phi of del u. So you start with d by du in the local chart u, which is a du. D by du is a coordinate system u. Apply the map d phi, then you get a tangent vector in R3. You take the inner product, and that's what you assign du, right? So this is going to be nothing but to differentiate. When you differentiate this with respect to u, you get minus fv sine u. Differentiate the second term, you get fv cosine u. Differentiate the third term, you get 0. So it's simply fv squared, right? Same thing with the other one. So you calculate du dv and you note that this is going to be 0, because the metric is symmetric. G12 is equal to G21. And the only other thing that you're left is to compute G22. So the answer should be this. So I'll leave it to you to compute, but this is a very simple combination. Perhaps the simplest question that we'll discuss. Okay. Okay. So the next question says that the geodesics are governed by this set of equations. So you have 2 equations, one for each of the variables. So effectively, this means you have to compute the Christoffel symbols and say that the Christoffel symbols are whatever they should be as governed by this formula. That's all, right? Because the geodesic equation is defined by the Christoffel symbols, that d2x by dt2 plus summation gamma dxj dt dxk dt. That's the equation. So again, this is a simple computation. I'll recall for you that the Christoffel symbols are given by these coefficients, gamma I, jk, and there's a half, and this is g raised to im, which simply means that this is the imth entry of the inverse of the Riemannian metric that you have. So we have we had the metric before. The metric is a diagonal metric, right? So the matrix associated to the metric is a diagonal matrix. So the inverse is also diagonal, and that means that G upper 1, 2 or G upper 2, 1, they're 0, because it's a diagonal matrix. So anyway, this is something I'll leave it to you to check. So if you calculate 2 comma 1, 1, it's going to be this. So a lot of things will cancel. Okay. And why is this 0? Well, remember you have 3 terms. So 2 of them will cancel because they are the same. One of them will survive, but why is this 0? Because remember G11 was f squared. F is a function of v, and x1 in our case is u. So d by du of fv square is evidently 0 because v and u are independent variables. So that's why this is 0. Okay, it's not because everything cancels there, because there is still one term left. But that's 0 because g11, and even the matrix itself is only a function of v. There is no dependence on u. So whenever I see a d by dx1 of anything, that's going to be 0. Okay. So here, well, you see these two terms, the first term and the second term, they're going to be 0 because these are off diagonal entries and they're 0. The only thing that you have here is this, but that's 0 because remember g22 is only a function of v and x upper 1 is our variable u. Okay. The only relevant thing that you are left with is this, and remember Christoffel symbols are symmetric. So gamma 1, 1, 2 is gamma 1, 2, 1. So you get 2f by f prime. So if you divide out by 2, you get gamma 1, 2 is f prime over f, but then you get gamma 1, 2, 1. So that gives you this equation, right? So this 2 here appears because you get one contribution from gamma 1, 1, 2, one contribution from gamma 1, 2, 1. Okay? All right, so that's it. So how about the other one? So I'll just quickly run through this because this is a routine computation. I might have done some of it in the class itself. It's your job to go back and do enough examples to know how to do it in the heat of the moment. So anyway, so I'll just leave you with this. So if you compute, you'll see that the gamma 2, 1, 2 is 0, but the diagonal terms in gamma 2 are of this form. So that implies a second equation. Okay, so that's not too bad. All right, so what are we heading towards? We are heading towards a characterization of geodesics on a specific surface of revolution. Okay, but before that, there's a typo here also. If you go back and look at your homework, or if you have it open, you can look it up even now. So the question in the homework said that show that if gamma is a geodesic, this is equal to the length square of gamma prime. But the length square of gamma prime for any curve is this. There's nothing to prove that. That is evident. Okay? The main point is this question is asking that if gamma is a geodesic, show that the speed of a geodesic is constant without resorting to the theory. So to keep in mind that this is a question which precedes the course in Riemannian geometry. So typically, this is something you might encounter in a course in geometry of curves and surfaces. So if somebody says, given this, show that this is a constant, you have to show that this is a constant because you may not have been used to or been introduced to a notion of geodesic when this is usually done. So you cannot say that, geodesics have constant speed, so this is evident. This is not. Okay, that's the point of the question. Yeah, so this is the corrected version. So you have to show that this is a constant provided gamma is a geodesic, meaning it satisfies these equations. So you have to deduce it from the two equations. So, well, the first thing is if gamma t is any curve, what is gamma prime t? Well, you simply just differentiate. So remember it was f cosine u, so it would be f prime v dv dt minus f sine u du dt and so on. And the last one is g, a function of v only. So to differentiate, you get g prime dv dt. So g prime here means dg dv. Okay, so if you take the norms, this is what you obtain. So the question really boils down to what I said at the very beginning, that you have to show that this is a constant. So how do you show a function is a constant? Well, one way of showing it is by differentiating this. Yeah, just hold on for a moment. Sorry about that. Okay. Yeah, so where was I? So yeah, so the point is to show that a function is a constant, it suffices to show that the derivative of that function is zero, identically zero. So that's what you do, right? This is just basic calculus. You differentiate this whole entire thing, and you see that when you differentiate this whole entire thing, with a little manipulation, this basically becomes the second of the two geodesic equations. But that holds anyway because gamma is a geodesic. So that's why the speed is constant. Okay? So yes, if you differentiate this, you manipulate a little bit, you show that that is 0, which means this is a constant function, which means speed square is constant. So any questions? So this is something most of you might have tried and got it. So there shouldn't be many questions regarding signs and everything because most of it is correct. So let me just make a remark. So again, the remark is what I just discussed earlier. This is a question that usually appears before Riemannian geometry. So the point is to show that this is true without using the theory that we have developed. And one can think of this as conservation of energy of a particle moving on the surface of revolution along a geodesic. Because this is, if you take the mass to be 1 and then if you normalize with a half, then this is like half mv squared or half m speed squared. Okay, so all right. So if there are no questions, move on. So this is also an easy one. It says show that meridians are geodesic. So remember, you have a surface of revolution, right? So surface of revolution is you choose a curve and then you just rotate it around the z-axis. The claim is that you look at the meridians. So what are the meridians? The meridians are those where you fix your u, say u equal to u0, and you look at your curve as v varies. So those are the meridians. And the parallels are going to be where you fix your v, which means you have fixed gv. So you're intersecting the surface of revolution with a horizontal plane, and you get a circle. Those are the parallels, and the meridians are the ones which are perpendicular to these. Okay. So meridian is simply defined by setting u equal to u0 and v equal to vt. Okay. But remember, it's not the image, it's really a parameterization of the curve. So what the claim is that I can find a parameterization of the meridian gamma such that it becomes a geodesic. Okay? So which means I cannot simply take u0 comma t, because u0 comma t may not even have constant speed. I have to think of u0 comma v, where v is a function of t, such that this has all the properties of a geodesic. Okay? That there's a small obvious thing to note here. So remember, what was the equation that we had? You go back, this was the equation, right? F prime square plus g prime square dv dt square plus f square du dt square. So a meridian has u to be constant. You fix your u to be u0. The only thing that varies is v, which means du dt is 0. So this term is gone. Okay? So I only have this term, which is what I wrote down here. Okay. So what does this tell us? This tells us, and we are assuming that the constant speed is 1. So set c equal to 1. So our equation becomes dv dt whole square is equal to f prime square plus g prime square, the whole inverse. Okay. Okay. So it's clear that a meridian satisfies this equation. Okay. This is almost evident. The first equation. So you want to check. So what we want. Okay. So you want to check what we get. So remember, I have to satisfy two equations for a geodesic. So if I go back, what is the first equation? Let me just go back since I have the luxury of slides, or not having the luxury of blackboards, I might add. The first equation is this, correct? And this is evidently true because u is constant. So du dt is 0, d2u dt2 is also 0. So both these terms are 0. So the first equation for a meridian is automatically true. The only thing that you have to check is this is true. Second one, right? And even in the second one, remember this term is 0, correct? So what you're left with is d2v dt2, that is one term, and you're left with this term, right? But even here, you should note that, so we'll get to that. So essentially, you have to prove this equation minus the second term. So I hope that is clear. Are there any questions regarding what we want to prove? We want to basically prove that the second equation is true for a meridian. All right. Okay, so let me maybe just go forward. So now, so that's what I just said. It satisfies the first equation. So let's differentiate this and see what we get. So if you differentiate, what do we get? Twice v prime, v double prime. That's what you get by differentiating v prime square. It's 2v prime, v double prime. What do you get by differentiating this? You get 1 over this thing with 2f prime f v dv dt. But now you see that you can cancel off dv dt from both sides. And you can cancel off 2. And what you get is exactly the second equation, right? This is exactly the second of the two geodesic equations. So a meridian is a geodesic. Okay. So I hope this is clear. Right? Okay, any questions? So what we'd like to do, so all of these are more or less straightforward up to this point for this question. What I'm really interested in, and perhaps what most of you might find really intriguing, is what happens for a general geodesic on a specific surface. So to introduce that notion, let's introduce the notion of a parallel. So what is a parallel? Remember, a parallel is going to be the curve obtained by intersecting the surface with a plane parallel to the xy plane. So it's like take z equal to a fixed height, intersect that plane with the surface. What you get is going to be a circle because your z coordinate is fixed, and then it's a circle of radius f of v, with placed at height g of v, and u is arbitrary. Okay. So you have a parallel, and then you are intersecting the parallel with the curve gamma. Okay. So here, I guess one has to say that gamma is a geodesic. So I haven't mentioned it here. I might have mentioned it in the homework, but this is not true for a general curve. So anyway, so you take a geodesic gamma, you intersect it with a parallel, and you look at the oriented angle between P and gamma. So let me just go to a picture because it will be useful. I should have included the picture here. This is the picture, okay? So this is a particular surface that you obtain by taking a paraboloid. So paraboloid is obtained by taking the graph y equal to x squared. So f of v is v, g of v is v squared. And if you take the graph y equal to x squared, which is like this, and you rotate, that's like spinning, right? Then it basically creates a paraboloid. So as you see here, this circle, or part of the circle, this is a parallel, P. This is a geodesic gamma, okay? And this is the angle beta. So that's what they mean by the angle between the geodesic and the parallel at the point of intersection. So for every point on the geodesic, you can look at the corresponding parallel, because if you are here, that determines the height, and at that height you intersect it, you get a circle, and you look at this angle. That's beta. So is this picture okay with everybody? So this is what I'm going to call beta. Okay, I'm going to come back to this picture in a few minutes. So let's go back. So that's the picture. So you have beta, and what is r of t? Well, remember, r of t is nothing but the radius of the parallel circle, right? So each parallel is basically a curve obtained by the intersection, but it's a circle, and the circle has radius f of v. So r of t is really f of v of t, and beta t is this angle. So the question says that the function r of t into cosine beta, so the radius into cosine, that is a constant. Okay. So this is also sometimes attributed to Clairaut's, called Clairaut's formula or Clairaut's law.